Good morning, CIE Education Working Group. All of you are champions of cyber-informed engineering, and today we'll focus on how that advocacy is already translating into concrete outcomes at the University of Florida. So specifically, we'll highlight UF's momentum in student-driven competition exercises, new module development, including human factors and microgrid scenario kits that are growing out of this initiative. Data from our first integrated course show a clear mindset shift. Students now view security as a design responsibility. They value engineered fail-safes and are eager to embed CIE into their real projects. And joining me today are two UF students who have been instrumental in leading CIE integration with me. The first is Paige. She's a Ph.D. candidate in the Material Science and Engineering's Nuclear Engineering program. And the second is Mary, who's an undergraduate in Industrial Systems and Engineering. So I thought I'd start with a first one slide just about the University of Florida. This is a repeat of one that I presented last year. So UF branded itself as an AI university in 2020 after a major partnership with NVIDIA and a donation from NVIDIA co-founder Chris Malachowski. And after this fall's upgrade, UF has now the most powerful university-owned supercomputer by any academic institution in the country. It's called HyperGator. We also have an AI across the curriculum initiative, which means that all of our 55,000 plus students get exposed to AI in their coursework. And there's a lot more as well. We've done a lot of AI hiring, degrees and certificates, events, and so on and so forth. The Herbert Wertheim College of Engineering at UF consists of about 11,000 plus students enrolled every year. We have 10 departments, 15 degree programs, and more than 10 research institutes and centers. And among these institutes, the Florida Institute for National Security, or FINS, where I am an associate director, is leading the CIE integration at UF. So FINS is an institute that started in 2012 and was relaunched in 2022 with a new mission focused on AI for national security. FINS is also leading the FINS Talent Pipeline, or FTP program, where we identify top domestic undergraduate students of all disciplines, immerse them in AI and CIE-based research, and fast-track them to internships in federal agencies, specifically those requiring security clearances, so that once they graduate, they're prepared to fill critical national security positions. And this fall, FINS also launched a new National Security Club student group, which Paige leads, and it also helped drive some of these CIE initiatives that I'll discuss. So I'd like to briefly outline some of the hurdles we hit while trying to weave CIE into UF's curricula. On the administrative side, and this is perhaps unique to UF, we've had a short-term president followed by 2 interim presidents, also 2 interim deans in our college, and 5 interim department chairs currently, including SICE, chemical engineering, environmental and civil engineering, mechanical and aerospace engineering, and material science engineering. All of this since early 2023. So that turnover makes it hard to lock in these long-term academic priorities. And faculty are also stretched thin. This is something that is probably common to all universities and institutions. For example, the upcoming ADA compliance deadlines are consuming a lot of our time. And we also lack ready-made discipline-specific CIE teaching materials. So with an already full course schedule, there's also resistance to adding new modules and course content, including CIE. In contrast, we found that on the student side, there are no systematic barriers. Our students are very eager, organized, and have active groups that are ready to engage in CIE. So because a lot of these obstacles sit with the administration and faculty capacity, we found the most reliable catalyst is actually our students. So their demand and Crossroutes initiatives are actually driving CIE integration at UF, despite a lot of headwinds. So the rest of the presentation is going to highlight CIE integration progress, particularly those where students have played an important role in the development. right, so sorry, I skipped ahead. We'll start with our competition exercises. The first one was developed by a master's student named Uthra in my department, ECE, and it's centered on a desalination plant exercise with 3 problems. Uthra previously worked in such a plant in India and could therefore bring a lot of practical familiarity with its equipment and operations that me and perhaps other professors couldn't. She created block diagrams that show the base plant, locations where AI could be integrated, and then the risks in doing so. And the development of the first 2 problems in this exercise set was supported by our CIE grant last year. And the final problem and its artifacts were completed during an independent study that Uthra did under my supervision last fall. Uthra graduated this semester, and she received 2 awards in part for the work she did here. One was from our UF International Center, and one was from the College of Engineering directly. Now, I've shared this exercise, the appendices with block diagrams, and the problem 3 optimization scripts in the working group box folder for those of you who have access. And you could find that by clicking the link that I embedded in this slide. And now just a few more notes on the 3 scenario-driven problems from our competition exercise. They were designed basically to walk students through what can go wrong, to what controls we can engineer, to how do we prove it works. And the plant contained distributed control systems as well as variable frequency drives. We consider cases with no AI versus having AI, both at the edge and at the cloud, for quality, dosing, pumps, health, and compliance. And we also examine attack surfaces that are mapped across 6 zones in the plant. Problem 1 considers an AI-augmented plant where students trace consequences of attacks, like sensor spoofing, man in the middle, poisoning, backdoors, and so on. And they're supposed to identify critical functions and quality impacts. They're supposed to try to map these locations and propagation across the 6 zones that I mentioned, and produce rich risk matrices and annotated diagrams, noting cases where the PID control may not trigger in time. They also are supposed to use CIE principles as their guides, especially consequence-focused design to prioritize hazards and interdependency evaluation to show cascades. The second problem gives 8 concrete attacks and asks students to engineer controls across the edge and the cloud and those different zones. They're supposed to compare AI at the edge versus at the cloud in terms of effort, cost, latency, and security, assess third-party versus in-house AI, and deliver an attack-to-control table, deployment comparison, and recommendation matrix. In this case, the CIE principles emphasize our engineered controls, layered defenses, active defense, and plan resilience. And in the last problem, we were inspired by the CIE-based linear program application that was discussed in one of last year's working group meetings from the implementation group. So based on countermeasures considered in problem 2, students are supposed to formulate and solve optimization models that minimize energy and chemical use under quality constraints, and then simulate normal versus attack versus CIE mitigated operations. And they're supposed to compare AI control versus fallback, report recovery time and performance loss, and recommend parameters that keep product water in spec under stress. So what success looks like is concise tables, clear location maps, and before-after plots that tie to accuracy, rigor, CIE application, clarity, and feasibility. We piloted parts of this exercise with our FTP student group to see how they could grasp and apply CIE. The first session, which was about 50 minutes, consisted of a brief motivation for CIE and a walk through the 12 principles. And then between sessions, we gave them access to our exercise document, which functioned as a primer for the plan architecture, AI attack surface, so they could come prepared for hands-on AI analysis, which occurred in the second session. In the second session, we asked them to form small groups to brainstorm problem 1, as well as problem 2, and then use the artifacts followed by an open share out to compare their different approaches surface disagreements, and to tie recommendations back to the CIE principles without getting bogged down into the theory. Overall, the students were impressed with the CIE framework itself, and I was equally impressed by how quickly they took to it. Several of the students, again highlighted on the right here from our FDB cohorts, Paige, Trevor, Carter, and Mary, they developed some of their own student activities and course materials, and those are going to be discussed next. So with that, let me hand off to Paige to discuss the second exercise.
Before Paige starts, Domenic, can you give us a couple of acronym definitions that we blew right past? Sure. Specifically, Tom was asking in the chat about the UF engineering curricula. Maybe this FTP acronym.
Okay, FTP stands for Finn's Talent Pipeline. That's our group where we're gathering these domestic students and we're training them in AI and CIE.
Excellent. Thank you.
Perfect. So as Dr. Forte mentioned, I've been leading the National Security Club at UF, and I got together with a few other student group leaders to organize an interdisciplinary CIE workshop where we invited students from the respective student clubs. So as you showed a picture on the other slide, we had Trevor, who leads the Florida Engineering Society student chapter, Carter representing IEEE. We had Mary from the Institute of Industrial and Systems Engineers chapter, and then we had Brianna, who was from our UF Engineering Innovation Institute Ignite Club. So before we planned the workshop, we really tried to identify our primary goals. So first, we wanted to introduce students to CIE principles by demonstrating the breadth of applications and by helping them to really develop the CIE thought process. Secondly, we hope to gauge student interest in the concept. So we really wanted this competition to serve as a pilot event to determine if there's sufficient interest to support a future competition or curriculum development. And finally, we wanted to develop an experience that was short, fun, and impactful, and that wouldn't necessarily overwhelm students with a long event or extensive technical content. So we aim to provide a fun and low-stakes environment that really fostered meaningful skill development and just left students with a positive and memorable experience. So those goals informed the following workshop design. The workshop occurred on a Wednesday evening and was about 1.5 hours long. We had about 25 students representing at least 7 disciplines who attended the workshop in addition to the student facilitators. Dr. Forte took about 15 minutes to introduce the motivation behind CIE and its 12 principles at the start. Then Trevor went into describing the escape room style games that we created to the students and gave them 30 minutes to complete it. And we played some 90s spy music in the background, so that was pretty awesome. We also tried to foster creative problem solving through an open-ended design. So the key to escaping wasn't necessarily getting the correct answer, but it really relied on students' ability to justify their answers using CIE principles. The results from the first theme to complete the game within the 30-minute time frame were analyzed by Dr. Forte and some of the other student expert leaders to see if we could declare them a winner, and they ultimately received a prize. And then he went on to informally discuss those solutions developed by the remaining student teams. So this is kind of an overview of the premise of the challenge. So Gator Grid Stadium is a fully smart, autonomous, and connected football stadium that is piloted at UF. Every major operation in the stadium is digitally integrated, including smart lighting, HVAC systems, automation, emergency alerts, autonomous security drones, digital ticketing, so on. And right before the stadium's first sold-out night game, the student engineering teams received a warning from a red team penetration test that they've found a way into part of the network, but won't tell them which one. The student's mission is then to secure the stadium before kickoff. So this activity is organized into 5 escalating stages. In each stage, the students applied CIE principles to make engineering and architectural decisions under that 30-minute time constraint. They prioritized critical systems, reduced attack surfaces, redesigned the network structure, and developed some fallback procedures, and then finally assessed whether the protections that they put in place can prevent cascading system failure. So for example, in stage one, teams could secure only 2 subsystems and had to prioritize those whose compromise would create the greatest physical consequences, such as the emergency alert system. So rather than simply protecting the most technologically complex systems, they had to prioritize those that would create the best or worst physical consequences. And so this really encouraged them to think in terms of consequence-focused design. Once the team was satisfied with its solution in a stage, then one of the trained student facilitators would review the rationale behind that decision and listen to their justification, and then could advance them on to the next challenge. So overall, the goal was to preserve safety, operations, and resilience for fans even when the systems were compromised. The teams were operated under realistic constraints, including the 30-minute countdown, as I mentioned. They had limited resources, and they didn't have entirely complete information. So we tried to mirror some real-world conditions that engineers may face in a real-world cyber physical system. So moving on from that, we deemed the event to be successful based on our post-workshop survey results. We received about a 30% response rate, and we determined that about 4.9 out of 5 average ratings found the event to be engaging, about 4.8 out of 5 found the event to be realistic, and all students found it to be about the right level of difficulty. They also said that they would attend similar events in the future and were highly likely to recommend an event like this to their friends. One of our first main takeaways is that incorporating CIE principles does not necessarily need to require a significant time commitment. So we met only a couple times to plan this workshop, so probably about 3 hours in total, maybe a little bit less, and we really enjoyed planning and hosting the activity. And so overall, this shows how valuable student training experiences can still be developed without a significant time investment. Secondly, there's also broad student interest in experiential learning events. This also aligns with successes that have been seen in non-CIE experiential learning focused events that have been hosted by other clubs. Based on other post-event conversations that we did have following this event, we found that participants were drawn to different aspects of the event as well. So some students were more interested in the academic content, so like Dr. Forte's lecture, while others were more engaged by the game. And so I think simulations like this one provide an effective balance of kind of conceptual learning with the hands-on application to ultimately attract a wide range of learning styles. In future iterations, I think it'll be beneficial if we really try to conclude with an impactful debrief highlighting how this decision-making framework is applied across a wide range of real-world disciplines, so that students leave remembering that real-world impact of CIE. And then finally, I think that this event just demonstrated overall the value of utilizing student organizations. Like I said, we engaged about 25 students from different disciplines, and we plan to continue to broaden participation by partnering with additional organizations and potentially expanding the concept into a larger scale competition at UF.
All right, I'll take back control. So the next part of our presentation focuses on our curriculum advancement activities. So I mentioned this in last year's presentation, that we began CIE integration in 3 ECE courses, which is my home department. We followed the CIE curriculum guide and started with our Intro to ECE course. For that, I recorded a video for this course, which is asynchronous, and it was used for the next course as well. The purpose of the video was to basically introduce students to CIE, its motivation, its principles, and walk them through an example. The other course is 3923. That's our junior design class, which I'll discuss more in the next slide. And I also integrated into my own course, which was advanced hardware security. And my goal this year was to integrate CIE into at least 3 more engineering departments at UF. And I'm happy to report that I exceeded that with 4 departments. So industrial and systems engineering, material science and engineering, engineering education, and ag and bioengineering. And this brings the total number of courses where we're touching on CIE to about 9. So in the remainder of the presentation, I'll talk about the feedback from our Electrical Engineering Design 1 course, as well as the course material that's driven by some of our FTP students, like Carter and Mary. And Mary will discuss her course. All right. So the Electrical Engineering Design 1 course is a 3-credit junior lab course where students design, prototype, and report on hardware projects. Very, very PCB design oriented and filtering oriented, that kind of thing. We integrated CIE as a module, which basically had 3 main components. The first is the starting point, which is the 3-part video series that I just mentioned. So students have to watch that. The instructor for the course also provided a journal article that discussed vulnerabilities in globalized electronic manufacturing, specifically the alleged implantation of tiny spy chips in supermicro motherboards. This was a major article called The Big Hack from 2018. It also discussed methods to detect these hardware Trojans and secure the PCB supply chain. Then students were asked to post 1 thought or takeaway from the CIE principles, as well as this activity on Canvas. And then they were supposed to respond to at least 1 other post. And we collected responses from these students from both the fall 2025 and spring 2026 semesters. And I've summarized some of the observations here. The first is a mindset shift. So across both cohorts, students abandon the old view that security lives only in code. They now see that security and supply chain risks are first-order security threats and should treat security as a design partner rather than just an add-on. They love some specific things. So first, several of them described how they were always interested in cybersecurity, but never knew how they could actually contribute to securing these systems in critical sectors. But now they feel actually empowered by CIE, specifically the deterministic controls and the even if resilience principle. And students also repeatedly praised the proactive, consequence-focused approach of the CIE framework. I also feel like we cleared some misconceptions as well. For example, security is IT only, hardware is automatically safe, and the fact that CIE can make a system unhackable, but rather it's really supposed to be lowering the risk of total failure. And the data shows that these myths were largely dispelled. Students also flagged some pain points, such as balancing security with cost and performance, securing the global supply chain, and this is, I think, is the most important one, lacking concrete implementation guidance, especially as we move forward in emerging topics like AI, IoT, and quantum computing. And lastly, the last thing that students are supposed to do in this course is their final project report. They're supposed to include a discussion of CIE best practices impacting their designs. So with this evidence in tow, I began my push for CIE into more courses, especially in the other engineering departments. So before handing off to Mary, I'll discuss one of the other courses. This one was developed by Carter and focuses on microgrid scenarios. Carter started his internship and wasn't able to join us on the call, so that's why I'm doing it. So the course that we integrated this into is a hands-on laboratory course that familiarizes students with practical aspects of conventional electrical energy conversion. And the scenarios that he developed are intentionally aligned with the equipment and the concepts that students are already encountering in each lab. This includes things like transformers, 3-phase systems, motors, relays, SCADA monitoring, and so on. So this allows the students to connect the security and resilience concepts to the familiar electrical engineering hardware. And the goal is not to turn the course into a security class, but rather to just introduce students to the idea that modern power and energy systems increasingly depend on digital control, automation, networking, and AI-enabled infrastructure. So Carter developed 6 scenarios, and they expose students to realistic operational and cyber-physical consequences, including unsafe voltage regulation, protection failures, manipulated sensor measurements, supply chain compromise, and the loss of operational visibility. And here are, again, a couple of the details. Each activity requires only about 10 minutes in addition, which is a minimal disruption to the actual current curriculum. A short scenario video is given to the students, and then it asks them to provide a brief discussion post or a reflection statement. Students are supposed to identify possible physical consequences, analyze dependency between cyber and physical components, and propose at least one engineering mitigation using the CIE principles, such as engineered controls, layered defenses, planned resilience, or consequence-focused design. And the broader educational objective is to help students think beyond traditional circuit functionality and consider how reliability, safety, resilience, and operational trustworthiness have to be engineered into future electrical energy systems. So this course, we plan to pilot this material in this course in the fall of 2026, and I hope to report that back to you next year. And with that, let me hand off to Mary.
Hi, everyone. Take control. My name is Mary. I just finished my 3rd year at UF, and I'm an industrial and systems engineering student. So I was working with Dr. Forte and Carter this semester on working to integrate CIE into our respective departments. So for me, that was ISE. I apologize for any noise outside. I was in the FTP program and hoped to get a job working in defense, and now I work for Northrop Grumman, and obviously you can't take calls there, so we're outside. When Dr. Forte initially approached me, I was looking at the coursework to see where CIE would best be integrated, and one of my favorite courses I was taking this semester was HFE, also known as Human Factors and Ergonomics. If you don't have a background on HFE, HFE studies how people interact with systems, and it designs to reduce human error. So any system, there are always humans in the loop. That's one of the big ideas in HFE. And we want to reduce human error. Normally when there's a system error, we don't like to blame the human. We blame how the system set the human up to fail. So now CIE assumes that cybersecurity has already failed and asks how the system can still support safe operation. I noticed a key connection between these two, and that's that cyber disruptions don't just break systems, they reshape the human behavior of, say, the operator in the systems. And both fields treat humans as assets to design around and not as liabilities. And one of the main differences between human factors and ergonomics as a whole, human factors focuses more on the cognitive side of operators, and ergonomics is more on the physical side. So say like workplace design and manufacturing spaces. So I wanted to focus more on the human factors side, dealing with cognitive load of operators. So like I said, this is the HFE model. So humans are a part of systems. They are in the loop, and there's goals going into a systems, and they want to perform. But for humans to act, there's information fed to them. And I noticed one of the biggest issues in cyber attacks was that information was delayed or disrupted or even tampered with. So I wanted to look at what happens when that information in the loop is compromised, and how does the human detect, interpret, and recover from that. So CIE will harden the information, which gives some resiliency and defense in depth to human factors. So when Dr. Forte initially presented CIE to the FTP pipeline, he said that I was initially confused on what the difference between CIE and cybersecurity was, but I really liked how CIE was applied earlier in the design cycle for systems. And then starting my human factors course this semester, I really liked how human factors principles are also applied early in design cycles for systems. So my takeaway from that was, if we design for cyber disruption early, from the cognitive side of the operator in the system and from the design side of the system, we can lower cognitive load of the operator and cyber attacks. So some more background on human factors and how some principles of human factors in my class tie into CIE. Most people think of cyber attacks as just technical problems and something breaks, you fix it. But in real incidents, we don't realize that cyber attacks change how people behave. So say an operator in a system, often before somebody realizes something is wrong. And then an operator can change how they act. And then that's when we initially see that something goes wrong. So for example, one cognitive human factors concept is alarm fatigue. Say operators in a control room deal with hundreds of alerts. When a cyber attack starts generating false alarms, operators naturally start tuning them out, and it's a rational response to be overwhelmed. But that's when a real threat can slip through. So in human factors terms, the response threshold, what we also call beta, shifts in the wrong direction. So if operators become overwhelmed and they don't know what's going on with, say, a cyber disruption, that means the response criterion to respond to something can go up and they get confused, and that can cause them to act wrong. Delayed data is also similar. So when information arrives late, operators are making decisions on a picture of a reality that's actually outdated, and they can't recalibrate their actions fast enough to keep up with what's actually happening. And manipulated displays are arguably the most dangerous because then they will take a wrong action. So if what you're seeing looks normal and you have no reason to question it, your ability to tell what is real from what's fake, which is what we call discriminability in human factors, just can disappear. So the overall point here is that these aren't just technical failures, they're human performance failures that cyber attacks can deliberately trigger, and that's why CIE needs to account for the human, not just the system. So a little more background on the course integration. So me, Carter, and Dr. Forte met every Monday this semester to discuss how CIE would align our course. So I took human factors this semester, and at the beginning of the course, it was more focused on the physical side. So I was concerned that I wasn't going to be able to tie it in, but then we went more into the psychological side of human factors, and that's when things really started to kick up for me. So I developed lecture slides, case studies, and quiz questions that connected CIE and HFE together. So just I gave some initial background in my lecture slides, like I just gave to you guys, and then I also mapped the existing CIE principles to HFE concepts to show students how the fields naturally overlap. And then our course layout, we have some case studies in between. So I also made a case study that connected the cockpit of a pilot and operators when a cyber attack happens in the cockpit to pilots, and how that connects to CIE. And I presented all of this to the professor, and he loved it, and he is going to pilot the integration next semester. Now, this is kind of a low commitment integration, so I sent him all of the materials, and he's picking out which principles map best to our content, and then he's going to send feedback so we can present it to you guys. So I'm going to dive in one of the examples from the PowerPoint I made. So this was Secure Information Architecture, Principle 3. So Principle 3, as you guys may know, is about designing systems so that the information that operators rely on can be actually trusted and verified. And this was one of the cases that Dr. Forte actually presented to me and Carter. It's called the Oldsmar case about a water plant in Florida. And it's a perfect example of what happens when secure information architecture is missing. So lie levels were dramatically increased, and investigators couldn't determine whether it was a cyber attack or human error because the logging and access history were incomplete. So the system, it couldn't tell its own story. From an HFE perspective, this is a big trust problem because when operators can't make decisions based on what their displays tell them, then they don't trust the system anymore, and they can't verify what is the truth and what isn't. So that doesn't just create a technical gap, it puts the operator in a bad position. So they can't respond safely to something that they can't affirm is real. So my takeaway from this, and most of the principles I map to, is that unverifiable information isn't just a cybersecurity failure. Most of these issues become human factors failures too. So I also map that to, say, design simplification. That is another big human factors principle, is that, say, when a display for an operator is very overwhelming and a cyber attack happens, they may not know how to react to that because they have so much information at their hands. So we need to figure out how to design these systems better so that humans can interact better when the system is failing, and then the system can degrade in a safe way. And hopefully that doesn't happen. So that is all that I have. I don't know who goes next.
Okay, perfect. Thank you, Mary, and thank you, Paige. So as we wrap up, let me just share where we're trying to head next year. First, we want to expand our reach. So we'll pilot some of the student developed materials that you saw into ready-to-use CIE toolboxes for our instructors. And we'll build on the momentum of the Gator Grid competition. So some discussion that Paige and the group have had is to kind of create perhaps a new CIE scavenger hunt type style competition. So this is hands-on challenges that let anyone on campus hunt for hidden digital risks in real-world systems. And throughout the year, we want to collect feedback from our students, faculty, and administrators, circulate a report so the university can see the impact in real time of learning about CIE and these different competition activities and so on. In July, so about 2 months from now, our team is also going to present outcomes at the FES ACEC annual conference. And we'll showcase some of these student-driven CIE innovations to a national audience. And finally, we'll pursue external funding and grant opportunities to scale and sustain these activities beyond a single academic year, and hopefully to more departments as well. Another thing that we want to do is, of course, deepen the curriculum. So as Ben mentioned in the last working group meeting, there's different levels of integration. We're mostly at level 2, which is case analysis and failure modes, but we'd like to move to level 3, which is analytical and computational models. So I'll probably do that specifically in ECE, both for my course as well as the microgrid course. So we can embed fully the CIE design hardening workflows into those courses. And the last thing I want to end with is just a call to action. So a lot of these advances don't happen without support. So if any of you believe in empowering the next generation of engineers to design safe and resilient systems, please consider donating to our FTP program and UF CIE initiatives. The link is embedded on the lower right-hand side. So your contribution will help fund curriculum development, competition prizes, and tools our students need to keep UF at the forefront of cyber-informed engineering. And with that, again, I want to thank Paige and Mary for all their hard work this past year in helping me with CIE integration, and for taking some time to help me present it today. And yeah, we'd be happy to answer more of your questions as well. Thanks, everyone.